Hello students, so I'm back with my next video of the chapter Human Eye and the Colorful World. In this video we'll be discussing about some natural phenomenon which occurs around us due to certain properties of light, like formation of rainbow, why the stars twinkle, why the color of the sky is blue. All these things we'll be discussing, but let me tell you that whatever I'll be explaining, it is just theoretical. If you really want to experience the actual phenomenon, you should go out and watch this phenomenon. And as you watch this phenomenon, don't watch it like a lame person. Because now that you know the reason, you will be knowing the reason why these things happen after watching this video. I request you that you should, when you go out and you see the stars twinkle, you keep the theory, let the theory come back to your mind, and you try to explore or try to reason yourself as to why that phenomenon is taking place. So let's begin. First we'll be discussing about formation of rainbow. So all of you have seen rainbow, where we see arc shaped structure which has all the 7 colors, vivjur, which we say, violet, indigo, blue, green, yellow, orange, red. But before understanding how a rainbow is formed, let us try to understand one phenomenon of light which is called total internal reflection. So total internal reflection is a special case of refraction. Now how it happens? Suppose we consider this ray of light. Let us consider that this ray of light is going from denser to rarer medium. So as it is going from denser to rarer, it will bend. It should have gone like this, but now it will bend away from the normal. So let this ray be number 1, let this ray be 1 dash. So it will bend away from the normal. Now if I lift this ray a little bit to this position, let's say this position is 2, this ray will come even downward. The refracted ray will come downward. So let us take this to be 2 dash. Now let me lift this ray still more so that the refracted ray passes through the boundary of the rarer and the denser medium. So let's say this is ray number 3. So this is, let's say, 3 dash. So for this particular angle of incidence, the refracted ray is passing through the boundary of the rarer and denser medium. So this particular angle of incidence is called the critical angle of incidence, or the critical angle. So what is critical angle? The angle for which the incident angle, the angle of incidence for which the refracted ray passes through the boundary of a rarer and denser medium. Now till here it's fine. Now if I lift this incident ray even more, let's say I take it to position number 4, then what will happen to this refracted ray? Instead of getting refracted, it will re-enter back into the same medium, following all the laws of reflection. So angle of incidence will become angle of reflection. So it will re-enter, this incident ray will re-enter back into the same medium, even though the other medium is a medium through which light can pass. So it will not go into that medium, but it will re-enter back into the same medium. This is called total internal reflection, which happens when light travels from denser to rarer medium and the angle of incidence exceeds the critical angle. Now you see, in my earlier video on prism, I told you that when white light, so suppose there is a prism, when white light is incident on a prism, then the white light will split into the 7 constituent color. The color, the 7 constituent color of white light is vivjur, V-I-B-G-Y-O-R. So violet, indigo, blue, green, yellow, orange, red. Now out of this, violet has the least wavelength. Last year you have learned wavelength is represented by lambda, least wavelength, the shortest wavelength. And red has the longest wavelength. Now when the white light will pass through any dense medium, these rays or these colors, they will bend through different angle. Now why they bend through different angle? If we try to understand in a very simple way, let's say that this is a particle And suppose violet light is coming. Normally light waves are not like this, but since when we say waves, this picture comes to our mind. So this concept is easier to understand. So let's say these are the waves of violet which are having very less wavelength. So when this wave is coming, so this is violet, and suppose red is coming. Red is having very long wavelength. It is having very long wavelength. Now out of this violet and red, which do you think will have a greater tendency to collide against this particle? So let's see, suppose violet, it is coming at a very close interval up and down with very short wavelength. So the tendency of this violet to hit this particle will be more. But when red comes, the red may go either above the particle or below the particle. So the chances of colliding with the particle will be less. So what basically happens is that violet undergoes maximum collision, and as it undergoes collision, it keeps on bending, and so violet will experience maximum bending, and red, since it will experience minimum collision, it will undergo minimum bending. So red will be on top, violet will bend the most. So this is how the splitting of light takes place when it passes through a prism. Okay. So actually there is one more activity given in your book. Let me quickly explain that, then we'll go to rainbow. Suppose we are placing two prisms, one upright, another one is inverted. Suppose a white light is incident on this prism. It will split into the 7 constituent color, and the lowest one will be violet, upper one will be red. When these 7 colors will emerge out and fall on this prism, they will, you know that light always bends towards the base of the prism, so they will all go towards the base and they will meet and they will emerge out as a single white light. So it is entering as white light and it is emerging out as white light. So if you produce the incident ray in the forward direction, we will find that the original incident ray has been laterally displaced, very similar to light passing through a rectangular glass slab experiment that we discussed earlier. Okay, so now let's come back to formation of rainbow. So this is called dispersion of light. So dispersion means splitting of light into its constituent colors. So when sunlight comes in, sunlight is constituent of 7 colors, we take it to be white. So when it is raining, normally when we can see rainbow, when it rains, suppose it's raining, the raindrops which are suspended in air, each raindrop acts as a microprism. Let us magnify one raindrop. So when the white light will pass through this raindrop, it will act like a prism and it will split into the 7 colors. The lowest one which will undergo maximum bending is violet, and the upper one which undergoes minimum bending is your red. So inside the raindrop, these rays will go and hit the other surface of the raindrop at such an angle that it will exceed the critical angle. So it will not emerge out on this side, but it will undergo total internal reflection. As it undergoes total internal reflection, they will get reflected and they will emerge out as 7 constituent color. On the topmost part of the rainbow, we will be getting the red color, and the lowest portion of the rainbow will be getting the violet color. So this is how, because these are made up of raindrops, the screen is made up of raindrops, and you can see this entire rainbow being formed. Okay, now one more thing is that if a question is asked that if there are 4 positions, suppose position A in front of the rain, position D below the rain, position B behind the rain, and position C above the clouds, at which position the probability of seeing the rainbow will be maximum? The answer will be A. That means when you have to see a rainbow, the sun has to be in front of you, and the sun has to be above your shoulder, and in front of you there should be the rain. That means the rain should act as a screen on which that rainbow will be formed. So if you are standing like this facing the rain, you are watching the rain, so above your shoulder the sun should be there, because the sunlight will hit the raindrops, split into 7 colors, and you can see the effect. So this is the case of formation of rainbow. Next we come to the next phenomenon, which is twinkling of stars. Now when we are talking about, I hope it's okay, yeah. So when we are talking about twinkling of stars, you have seen twinkling of stars. So twinkling of star is actually a case of atmospheric refraction. Now how it happens, suppose there's the observer and there's the atmosphere. We can think our atmosphere to be made up of many layers. The lowest layer will be the denser one, and as we move up, we know that air becomes rarer and rarer. So the upper layers will be rarer. Now when the rays or the light ray from the stars, it passes through these different layers, they are passing from rarer to denser medium. So as they are passing from rarer to denser medium, the light ray will bend towards the normal and it will keep on bending and ultimately reach the observer. But for the observer, light seems to travel in a straight line. So for him, an apparent image of the star will be formed here. So actually the stars where we see them, that is not their actual position. It is slightly away from that. Actual position is slightly away from that. What we see the stars at, that is the apparent position, and that is due to atmospheric refraction. Now why the stars are twinkling? Now these layers of the atmospheres are not fixed. Layers does not mean troposphere, stratosphere, ionosphere, not these kind of layers, but the troposphere itself, we can imagine it to be made up of different layers. So these layers are not having fixed boundary. Due to wind and due to rotation of the earth, the boundaries of the layer will keep on mixing and the densities will keep on changing. As the densities keep on changing, this apparent position of the star keeps on changing. And star, you know, it appears to be a point size object. Stars are actually big, but for us they appear to be point size object. They don't appear to be big size object like the moon or the sun. So what happens? Suppose at this moment the star appears to be here. At the next moment, due to change of density here, this apparent position will change and the image may be formed at a new position. So the earlier image disappears and the new image is formed. So nearby the multiple images are being formed at different times with the earlier image getting deleted. So it gives a kind of on-off effect, which we call the twinkling. But the question arises, why we don't find that the moon is twinkling? Because of this reason. Moon being near to us, it is quite a large object in the sky. So what happens is that here also, for the moon also, same process will take place. But since its size is big, even though its apparent position will change, it will not change to a greater distance. Only the boundary will change a bit. Suppose now the boundary is appearing to be here. In the next moment, maybe due to change of density of the layers, the boundary will change from here to here, and this side it will change from, let's say, here to here. So the boundary keeps on changing, and therefore on a full moon night, if you observe a moon, you'll find and keep on observing the boundary, you'll find that the boundary is quavering. Quavering means shaky. It's not a fixed boundary. It is due to this atmospheric refraction. Now practical, I told you in the beginning of this video that we need to understand these things on a practical level. So from your practical experience, you'll observe the sky and you see that when the twinkling effect is more, generally when it is a windy night, the twinkling effect is more. The reason is that when it is a windy night, the change of the density of these layers will keep on changing very rapidly, and the position of the star will keep on changing rapidly, thereby twinkling effect will be more. Another example of atmospheric refraction is early sunrise and delayed sunset. So suppose this is the observer and this is the horizon. Horizon, you know, that is the imaginary line where the sky and the land seems to meet, or the sky and the seas seems to meet. If you stand near a seashore, you'll find a line where the sky seems to touch the water. So that's called the horizon. Now suppose the sun is below the horizon. So actually the person should not be able to see it because it is below the horizon. But let's say the rays of the sun is passing from the rarer layer. We have already discussed the upper layers are rarer and the lower layers are denser. So it is passing from rarer to denser medium. So it will keep on bending towards the normal. It will keep on bending towards the normal to ultimately reach the observer. But for the observer, what I told here, the effect is created as if the light is traveling in a straight line. So an apparent image of the sun will be formed above the horizon. So though actually the sun is below the horizon, but for the person the sun will appear to be above the horizon. So we can actually see the sun much before the actual sunrise, or even after the sunset has taken place, actual sunset, still the sun will appear above the horizon for a certain duration. So what is that difference? That difference is of 2 minutes. That means after the actual sunset, even after 2 minutes you can see the sun above the horizon. Even before the actual sunrise you can see the sun 2 minutes before the actual sunrise. So in a day you can say for an extra 4 minutes, 2 minutes in the morning, 2 minutes in the evening, you can see the sun above the horizon. So next phenomenon that we'll be discussing is another interesting phenomenon, that is why sun appears to be red during sunrise or sunset. So during daytime it's not advisable to see the sun, but if with a solar filter, if you can see, the sun appears to be whitish, but during sunset or sunrise it can be safely viewed and we see the sun to be red in color. So first let us discuss that, then we'll discuss why the sky seems to be blue. So at sunrise the sun rays are entering, so this is the thickness of the atmosphere, it is uniform thickness throughout. But at sunrise or sunset, because at the horizon the sun rays are entering obliquely. Suppose there is a block, if the rays enter directly, this is the distance traveled by the ray through the block, and if the rays enter obliquely, this is the distance traveled by the rays. Okay, if the rays enter obliquely, this is the distance traveled by the rays. So when the sun is at the horizon and the sun rays are entering obliquely, this is the distance which the sun rays covered through the atmosphere. And at noontime, when the sun is overhead, since the sun rays are entering perpendicularly, so the distance traveled by the sun rays through the atmosphere is much lesser. So what happens is that, so all the 7 colors are passing through the atmosphere, and atmosphere has different dust particles and all. So when the light will hit these dust particles, the sunlight will get scattered. So this is an example, or this is an application of scattering of light. This is due to scattering of light. So the light will get scattered out. Now I told you red has the longest wavelength. So if there is any particle, the chances of this wavelength or this red light hitting this particle is very less. And violet, it has short wavelength, so the chances of violet hitting the particles will be much more. So as the sunlight travels through the atmosphere, violet, indigo, blue, they have short wavelength, so they simply scatter out, and as they scatter out they lose their energy and they are not able to reach the observer. But red, having the longest wavelength, it undergoes minimum scattering, and due to minimum scattering the red color from the sunlight is able to reach the observer, and therefore the sun appears to be red. So if you observe, again I am telling you, you should move out and observe this phenomenon, then you will understand it perfectly. So as from the noon, suppose the sun is proceeding towards sunset. So you observe how the color of the sun changes. From whitish it will become yellowish, from yellowish it will become orangish, and at the end it becomes totally red. Because at the end, means just before sunrise, after sunrise or just before sunset, the sun is at the farthest distance, and so only red light will be able to reach. Even orange is also not able to reach, and therefore the sun appears to be red. During noon, why it appears to be whitish? Because during noon the distance that the light is traveling through the atmosphere is less. So here also no doubt scattering will take place, but due to the short distance all the 7 colors are able to reach the observer. That's why the sun appears to be whitish during noon. Now what is sky? Sky is the space above us. Okay, so in the atmosphere different colors are getting scattered. Sunlight का जो अलग-अलग color है वो scatter होता है. Now out of all the scattered colors, our eyes are more sensitive to blue light. So यहाँ जो सब color scatter हो गया, even blue is there and all the other colors are there, but our eyes are more sensitive to blue light, and therefore the sky, that is the space above us, appears to be blue. So that is the practical application. Now this has another practical application in our day-to-day life. You have seen danger signal, you have seen stop signals, you have seen the backlight of cars. No matter how costly is the car, the backlight will always be red in color. Why it is so? Why the danger signals, stop signals or the backlight of the car is of red color? This is the reason, because red having the longest wavelength, it undergoes minimum scattering and it is able to reach the farthest distance. And reaching the farthest distance means from afar it will be visible and it will give an indication to the person that there is something there. Because we don't need the red light for brightness, we need the red light just as an indicator. So it will indicate that something is there to the person, and that is the reason why red light is used for all these purposes. So I hope all this phenomenon, formation of rainbow, the early sunrise, delayed sunset, twinkling of stars, and why the sun appears to be red during sunrise or sunset, all these concepts are clear to you through this video. Thank you so much.